objective 4 here, which is going to be writing decay equations. We're mostly going to focus on natural transmutation, but we will do a few that deals with artificial transmutation. So first off, what's the difference between the two? Natural is always going to occur with unstable atoms. You're always going to see the one unstable nucleus to the left of the arrow, and then you're going to see the alpha beta positron particle that gets emitted, and then you're going to see the new element that forms. So again, you'll usually see us writing these as the unstable nucleus, the particle it emits, and then what it transmutes into. Now with artificial, this occurs generally with stable atoms, and they have to be hit with or bombarded with a high energy particle, which creates or causes it to become unstable and then undergo transmutation. So in this one, we have the stable nucleus plus our high energy particle, like an alpha particle, beta particle, and neutron, and then it's going to transmute into something else. So you'll always see 2 on the left, and then you're going to see it transmute into one thing, or sometimes it will have an extra particle that gets released in that process. So in any of these, when we're writing our decay equations, it's going to be important to remember that your mass number is up on top, where the A is represented here, and that the atomic number is on the bottom, and that's always going to determine what element it is. That's where I'm going to get my symbol every time I come up with a new atomic number for the new element that's formed. When writing our decay equations, this is different than balancing regular chemical equations. We're going to be balancing the atomic numbers on the bottom, which are essentially the charges, and then the mass numbers on top. So again, it's different if you've done balancing already. So the sum of the atomic numbers or the charges on the left must equal the sum of the atomic number or charges on the right. And same thing with the mass numbers. The left have to equal the sum on the right. So this is an idea of it follows the conservation of mass and then also the conservation of charge. All right, so what do I mean by that in terms of our equation here? So I'm going to look at just the top numbers here. So on the top, I have 238 on the left. Think of the arrow as your equal sign, so it's going to equal. Okay, and then I'm going to look at the 2 top numbers on the right. The sum of these has to equal, the sum on the left, and it does. So 234 plus 4 gives me 238, which is equal to the left-hand side. If I look at the bottom, let me just change this just so you can see this differently. Okay, I have 92 on the bottom right here. Okay, the arrow is my equal sign. This is going to have to be equal to 90 plus 2. So I'm just looking at these bottom numbers, which when I add those together, I get 92. So 92 is equal to 92, and those match up. So I'm going to be able to use this to help fill in missing information, to figure out which element I transmute to. With our natural decay equations, again, we're starting with an unstable proton to neutron ratio in a nucleus, so it's going to undergo this decay to become more stable. Because it's natural decay, it's going to be the only thing on the left-hand side, and I'm going to balance everything. How do I know what type of decay it undergoes? We're going to be using table N. So table N has the decay mode up here, which is going to help us tell, is it beta, alpha, positron emissions? All right, so we're going to first look at a couple examples together. So here, our first one I'm telling you is alpha decay. So plutonium-239, which if I come over to table N, I'm going to see plutonium-239, okay, and it's showing me alpha decay. Okay, so that's how I know it's alpha decay. I'm also going to need to know the atomic number. So I know it's 239. I'm going to come down here, and here's my plutonium right here. Okay, so I know the atomic number for plutonium is going to be 94. So when I come over here, I'm going to have plutonium symbol, Pu, the 239. Actually, I'm going to put the 92 on the bottom. Where's that 2 there? And I'm going to put the 239 up at the top. Okay. All right, then I'm going to come over and I know it's alpha decay. So I'm going to fill in, I'm going to just do this in black for the time being, is that alpha particle. And an alpha particle is 42He. How do I know that? Well, if I come over here to table O, so it comes after table N, I can see that my alpha particle has this notation. Okay, 4/2He. You could also use the other notation there, but I usually pick the first one. I'm going to fill that in here. So this is the particle that it emits. You can do it in either spot. I'm just writing it first because that's one part that I know. Okay. All right, so then I need to do some math here. So I'm going to do the top number first. Okay, this top number is going to be 239. So I'm taking what's on the left. Then it's my arrow equals 4 plus x. Okay, so I know that this number up top has to be able to equal x here. So that means that 239 minus 4 is going to give me 235. Okay, then I'm going to do the bottom number. So in this case, I have 92, right, over here. The arrow is my equal. I have 2 from the alpha particle, plus I'm just going to use y just to change the variable. So I know this bottom number has to equal y in this equation. So 92 minus 2 is going to give me 90. Now, the biggest mistake is that students are going to put PU as the symbol here. It's probably what I see the most often. But as soon as that bottom number changes, 90 is going to tell me what my symbol is. So if I come over here, oh, I wrote down the wrong thing over here. This should have been 94. So if I change 94 here, sorry guys. Okay, and that was your 2 there. This would have been 92. Okay, so in this case, I'm looking at 92 is going to have the symbol U. Okay, and then this is going to be U here. Okay, so just be careful with that initial symbol here. Obviously, me writing it down wrong was going to throw things off, and I recognized that when I realized that instead of just moving 2 spots over, I was moving like 4 spots over. So that's what told me that was wrong. Okay, but the equation, the process is going to be the same. All right, cobalt-60 is a beta decay. So cobalt-60 would be CO. And then I'm going to put the 60 on top for the mass number, which just for time, I'm going to keep that green. Okay, I'm going to come over to my reference tables. I'm going to find cobalt. Cobalt is up here. Okay, it has the atomic number 27. So I'm going to fill that in on the bottom. Okay, a beta decay is going to come from table O. So beta right here is 0 over -1 E. And that -1 is going to become important. So 0, -1 E. So when I go to fill in my new element, I'm going to first do the top numbers. So I have 60 on top has to be equal to 0 plus x. So I know my top number is 60. On the bottom, I'm going to have 27 has to be equal to -1 plus y. So why is that important? When I go to get y by itself, I have to end up adding 1 to each side in order to get this to cancel out. So y ends up actually being equal to 28. And that should make sense that 28 plus a -1 will give you 27. Okay, so be very careful with beta decay. It's the hardest one, I think, out of the group for most students. Now that I know it's 28, I can come over here. Atomic number 28 is no longer cobalt because you remember atomic number changed. So this would be now nickel. Okay, and then with this positron decay, we have iron 53. So iron is Fe 53. If I come over to the periodic table, iron is 26. Okay, it's undergoing this positive beta decay, which is a positron. So if you come over, to table O, that symbol here is going to be almost the same as a beta particle, except has a +1 on the bottom. So I'm going to fill that in here, 0 plus 1 E. Okay, so then with this part, I'm going to fill in my missing variable. So 53 is equal to 0 plus x. So I know my top number is 53. And then the bottom is going to be 26 is equal to 1 plus y. So in this case, y is going to be 25. And when I come over to my periodic table, 25 is Mn, manganese. Okay, so those give you like the 3 examples. So what I would like you to do is to pause the video, see if you can use table O, but also table N to look up what type of decay it's undergoing. So you can pause it and then come back and actually check over to see how you did. So let me go through what you should have been doing and hopefully got to the correct answer. So in this first one, we have francium 220. Okay, I'm jumping over to the side here. Francium is 87. So I'm going to put 87 on the bottom. If I come over to table N, Francium 220 is undergoing alpha decay. So I'm going to be filling in my alpha particle symbol. And then from there, it's balancing the top numbers and the bottom number. So your top number should have been 116, and your bottom number should have been 85. Now check your symbol. Did you make sure you didn't write down francium? 85 is going to be AT over on the right-hand side. So you're going to see me fill in AT there. Okay. All right, moving on to the next one, neon 18. So I'm going to fill in neon 18. I'm going to make sure I go get the atomic number, which is over on the right-hand corner, number 10. Okay, I'm then going to be looking at table N. Neon, it's right here, 19. I see a B with a little plus. And say you don't remember what the symbol is. You're going to go down to table O. Okay, B with the little plus is going to be this symbol here. So 0 over plus 1E. So when I go to do the math here, I'm still going to have 18 on the top. The bottom is going to be 10 is equal to 1 plus Y, which means 9 is going to go on the bottom. And when I check 9, 9 is going to be over here, fluorine. I'm going to fill in my symbol, fluorine. So again, when that bottom number changes, the symbol must change as well. And then the last one in this natural transmutation set is cesium, 137. So I'm going to find cesium on here. Here I have cesium right here is 55. Okay, I'm going to look at table N for cesium. Sorry. Okay, this is undergoing beta decay. So I'm going to have 0, negative 1E. So the top number is easy, 137. When I look at the bottom, it's going to be 55 is equal to negative 1 plus Y. So in this case, Y has to go up 1. So this is going to be 56. And again, making sure I check my symbol. 56 is BA. Okay, and that would complete that natural transmutation. So it's a lot of work in terms of using table N, table O, your periodic table, and being really careful with your math and making sure you're balancing mass and charge. For artificial transmutation, this is really just filling in the missing particle from an equation using the same strategies. So in this first example, and this artificial is, again, we're forcing the transmutation to occur with some high energy particle. So in A here, carbon-14 isotopes forms when your nitrogen is bombarded with a neutron. So I'm going to use the same strategy. I'm going to look at the top. So I have 14 plus this one from a neutron is equal to 14 plus X. Well, if I look at that, I'm going to end up with X being equal to 1. So I'm going to fill that in the top. Let me actually change colors here to blue. Okay, on the bottom, I have 7 plus 0. So I'm looking at all the bottom numbers going across is equal to 6 plus Y. Okay, and I'm going to fill in a 1 on the bottom there. So I have a 1 over 1, which we're not as familiar with. So I'm going to check one of two places. I'm always going to check table N. See if you have that there. So I do see 1 over 1. And as you'll see, the symbol will actually show you that it's a hydrogen nucleus, which essentially is just a proton, the same thing. So we're going to fill in that symbol, either one. The 1 over 1 is going to be just an H in our case. Okay. All right. So again, it's just balancing the top numbers and the bottom number. And then finally here, I'm going to have, let me switch this to green really quick. I'm going to have X plus 4 is equal to 1 plus 30. Okay, so in this case, I have 31 minus 4 is going to be a 27 on top. And then on the bottom, I have Y plus 2 is equal to 0 plus 15. So 15 minus 2 is going to give me 13. That 13 I'm going to use off the periodic table. Okay, right here, 13 is aluminum. And I'm going to fill in that symbol for aluminum. So again, making sure that bottom number always determines the symbol if I don't find it on table N. So one last thing on your own, go through and just answer these last two questions. You'll see them pop up in the play posit. So which equation represents natural transmutation? Okay, first off, you want to see the nuclear notation. So C and D, we're going to cancel out. And if we look on the left here, B is the only one where you have just one on the left, giving off, in this case, a beta particle and changing into nitrogen. So B is going to be your answer. This top one would be an example of artificial. Okay, you have boron that's getting hit by an alpha particle to undergo the transmutation. All right, which example is official? example of artificial transmutation. So again, B and D in this case are just regular chemical equations. There's no transmutation going on. This bottom one, calcium, hydrogen, oxygen, are still calcium, oxygen, hydrogen at the end. So I'm looking at A and C, actually I can cancel out too, sorry. So that leaves you with B in that case. You have beryllium getting hit by an alpha particle, which is what's going to make it artificial, and transmuting into carbon. Okay. All right, we're going to keep working on these decay equations. So just make sure you got your reference tables ready to go.